Okay, so now we're going to talk about valence bond theory. And I'm going to skip through some of this because in my regular lectures that you have access to, I go over them in more detail. I'm also going to post several different YouTube videos from other people who invest in doing a lot of cool graphics and stuff so that you can see this better. It's really hard to just draw and describe, but I'm going to give it my best. So there are different models of bonding. Lewis theory, or the Lewis model, is the simplest, the easiest to understand, but it's also a gross oversimplification. It's still useful because it works a lot of the time. The more advanced theories apply quantum mechanics. And so we're going to look at two of those. I'm only going to talk about one of them today, the valence bond theory. And we're going to look at this in a very qualitative manner. We're not going to get into the math of it. So, quick review. We understand that electrons reside in quantum mechanical orbitals that are localized on individual atoms. Those are s, p, d, and f atomic orbitals. So when we have two or more atoms bonded together in a molecule, those orbitals can hybridize. Please pardon the dog noises in the back. Thank goodness you can't see what they're doing. So what happens when two atoms approach each other to make a bond, we've got a lot of complex interactions between the nuclei and the electrons. And so a chemical bond will form if the energy of the system is lowered by the interaction. Otherwise, it will not. So if we look at two hydrogen atoms approaching each other, here's the distance between the hydrogen atoms. So this is where they're further apart, and this is where they're getting closer. And this would be the nuclei actually touching, which can't happen. As these two nuclei get closer together, their orbitals will begin to overlap, and that will cause them to be attracted. And so we see the energy as they get closer, the energy is lowered. Like rolling down a hill, this is going to be a good thing, lowering the energy. And when we get to this point, this particular distance between them, we see that the energy is at a minimum. And if they get closer together, then they begin to push each other away. They begin to be repulsive. And so if you think about human interactions, this happens as well. You might see someone who seems interesting and you get closer to each other, and then you realize, well, this person's really attractive, I really like you, and so you get close and you start talking to each other, and then you find out that this person is a close talker, right, and is in your space talking to you too closely, and you're like, back off, right? Because there's this social distance, not our current social distance, but our normal social distance, measured more in inches than 6 feet, where people feel comfortable talking to each other, right? And so this is the comfortable spot. So what happens is that atomic orbitals, each containing one electron, can overlap and form a new hybrid orbital, and those electrons can spin pair. They orient with opposing spins. This usually happens from two half-filled orbitals. And so as those two atoms approach, the orbitals overlap and the electrons pair up. So in valence bond theory, we define a chemical bond as the overlap of two half-filled orbitals with spin pairing of the two valence electrons. So let's look at how that happens. We're going to look at sulfur and hydrogen here. And here we have the orbital diagrams for sulfur and hydrogen's valence electrons. And so we see that the sulfur atom has two half-filled 3p orbitals. And so we can imagine one of these half-filled orbitals overlapping with the half-filled orbital of hydrogen, and the other half-filled orbital overlapping with the half-filled orbital of another hydrogen. And so this is an illustration of that. Here's the sulfur. The blue is the s orbital. That's got 2 electrons in it. That's this guy over here. And then this is one p orbital, and a second p orbital, and a third p orbital. This one is filled. That's this lone pair here, or that's this pair of electrons here. But these other two have 1 electron. And here's hydrogen with its s orbital that has 1 electron. And so hydrogen's half-filled orbital overlaps with sulfur's half-filled orbital and forms a bond. And this one does as well. And so we're like, well, okay, that's not so bad. If we look at the actual molecule, the bond angle is 92 degrees. And valence bond theory here is predicting 90 degrees. Vesper theory doesn't give us an exact number, but it does say it's less than 109.5. 92 is definitely less than 109.5. Could you guys take that outside? Can you go outside and do that? So this seems to be working okay. So let's apply it to another molecule.